Linear inequalities attempt to mix together everything we know about lines with everything that we know about inequalities. So obviously we have this category of lines information: slope, intercept, point, slope, standard form, intercepts, vertical lines, horizontal lines. We have all of these options for graphing and all of this information that we need to consider. And then over here we have all of the information for inequalities: when to turn the inequality and face it the other direction, which way are we supposed to shade. So what we're going to try to do with linear inequalities is marry that information together and look at it all at once, as opposed to looking at them separated from each other. You might remember that when we solved inequalities way back earlier in this course, that we would end with something like x is less than 4, and we would place that solution on a number line and we would shade to the left. The reason that we were able to use one individual number line is because we only had one variable that we needed to worry about. Linear inequalities change the conversation slightly. Instead of looking at one variable by itself, we're instead going to look at the relationship between two variables and when are the two of them interacting together to make this inequality true. So for the purposes of getting started, let's take a look at our first example, which is y is less than 6 minus 1/2 x. Here is the line 6 minus 1/2 of x. That's our green dotted line. You'll notice that the line is dotted. We'll talk about that in a second. And you'll notice that we have shaded everything that is below that line. Think about what this is actually saying. This is saying I want all of the y's that are less than that line. So it makes sense that all of my shading is happening down here. I don't want it up here. I don't want all of the y's that are greater than that line. I want all of the y's that are less than that line. Now that line itself is dotted. The dotted line is an indication that those points are not actually part of the solution. That is simply the boundary line where the solution region ends. Think of these dotted lines the same way that you would think about an open circle when we did our one variable number lines. We're saying that that's where it starts. We're not saying that that's part of the solution. If you want it to be part of the solution or need it to be part of the solution, simply add an equal to, and now we have a solid line. And we can see that the point 0.6 and the point 12.0 are both part of the solution space now. When that equal to wasn't there, I go back to the dotted line. I could still click on those points, but I have to recognize that they are not part of the solution space. The decision that you make in terms of the direction that you're going to shade, I would recommend that you always make sure you have y by itself and you read these inequalities from the left to the right. That is typically the easiest way to do it. If you have it solved for y and you read y as less than, that's an indication that you need to be below the line. If you have it solved for y and y is greater than, that's an indication that you need to be above the line. And we can see that if we flip this inequality the other direction, now I'm shaded above. Same exact line, same exact boundary line, same dotted because it's not equal to, but we're shading in the space above. The decisions that we make regarding the shading hold regardless of the type of line, with one exception. If we look at a horizontal line, here's the horizontal line, y is greater than or equal to 4. You'll notice that the boundary line is solid, thank you to the equal to. And you'll notice that this is saying I want all of the y's that are greater than or equal to 4. Any point that you click on in this space, or any point that you can identify in this space, here's the point 2.8, here's the point 6.6, here's the point 10.5, would be right there. You'll notice that the common feature that they all share is that y is greater than or equal to 4, so it makes sense for us to shade above. The one exception to our above and below rule is not the horizontal line, but rather the vertical line. If we draw a vertical line, we want to use the same kind of interpretation that we used for the horizontal line. In the case of a vertical line, we have a dotted line, thank you to the no equal to, and we're simply saying that we want all of those points where x is less than 6. So it makes sense for 6 to be our boundary line. Any point that's over in this red space, and if we zoom out, you can still see that red space is growing and growing. It's not just confined to what was originally on the screen. Every single one of these points, even if I go negative 60, 20, and I'm way over here on the left, I'm still getting that their x value is less than 6. Once I cross over that boundary line, that would no longer be the case. So this is the one exception where you can talk about shading to the left and shading to the right. And despite the fact that if you were to draw a really steep line, something like y is greater than 19x, you can see the steepness of that line. I still don't want to talk about left and rights because I don't want to get into the habit of thinking that the shading is going to happen on the sides. The shading is actually happening above. And you can see that by putting your finger or the cursor on any point. Here I've chosen the point 0, 0, and then pointing up. And since I pointed up, I'm into the shaded space. So that's where all of my solutions are. If it was less than, I would point down, and I would expect the shading to be on the other side of the line. Not right and left, but rather above and below. So in summary, linear inequalities are very simply graphed. We use all of the information that we already know about lines, and then we make a decision of how to represent all of the other solutions. Do we represent all of the other solutions with some shading? Do we need a solid line or a dashed line? And do we make that decision about above and below? Or are we the one case where the decision is left and right?